Okay, Calc BC. Let's see, Unit 3, Day 1. So extreme values. So this is a review of some material from Calc AB. Absolute max min. Another word for absolute max mins are global maximums and minimums. I don't think we use that term that much, but let f of x be a function over the domain D. FC is an absolute max if and only if the value at FC is greater than or equal to all the other values on the domain D. That doesn't mean endpoints. Domain D, the domain could be all reals. So this is just kind of leaving it out there. So the other possibility is that you have a minimum, and that's where f of c is less than or equal to all the other values. Locating absolute extrema. One of our main tools, the extreme value theorem, EVT for short, not something to don't write it as initials on free response. And it says that if f of x is continuous, so there are some requirements to use an extreme value theorem, and on a closed interval, which means you have endpoints, then it contains an absolute maximum and minimum. You're guaranteed. That's one of the things. You're guaranteed to get a maximum min on the interval. The candidates, the places to consider, are the endpoints and the critical points. And the critical points are specifically where f prime equals 0 or undefined. It could be a sharp corner or cusp. It could be a smooth peak or valley. Relative or local extrema, relative maxes and mins, are like the peaks and valleys of a curve, which is very, loose kind of naming for it, not technical, but if you have a curve and you're like, well, here's a peak, here's a valley, a local min, relative min, right? This would be a relative max. Here's another peak, relative max. So f of x has a local maximum at c if and only if the value of c is greater than or equal to, for all x in some open interval containing c. That just means, in the immediate area if it's the highest point. Whereas the previous one for absolute is for all x in the domain. This just is some interval right around it. And min would be if f of c is less than or equal to all the points on some immediate open interval. Now, the way we identify these, without actually seeing a picture of the graph, is to really just look at their slopes. So you have positive slopes to negative slopes. Well, if you go from positive slopes to negative slopes, you had to be at the peak. You're going up, then you go down. You had to be at the top. If you go down and then you're going up, well, you got to be at the bottom. If you're going up and then you're going down, you got to be at the top. So it really comes down to just looking at a change in slopes from positive, negative, or negative, positive. And that's called the first derivative test. And it says if derivative changes from positive to negative, then you can get a relative max. If it goes from negative to positive, you're going to get a relative min. And you look for this to happen at critical points. So where the derivative equals 0 or undefined. It could be a smooth peak or valley or kind of a sharp one. We usually use a line check to help us identify these if we can't have a picture. And so we'll practice a couple of these in the back. But this isn't something to memorize. If you're going up, positive slope to negative slope, you got to be at the top. If you're going down, then you're going up, it's got to be a low point, right? That shouldn't be something to memorize. The second derivative test says that if the derivative equals 0 or undefined, so that means you have a critical point. So you got to know you have a critical point, and the second derivative is positive, which could also be interpreted as concave up. And f of x has a local what? Max or min. Again, this is not something to memorize. If you just draw a concave up curve with a critical point, then that is clearly a relative min. Now this gets into, or local min. Now what this gets into is that actually the derivative cannot be undefined for second derivative test because there is no concavity at a sharp corner. So it wouldn't even make sense. So it's specific critical point. Only the smooth critical points can use second derivative tests on. So the other one is your critical point. It's concave down. Just draw a picture. Don't memorize this. Draw a picture. Here's your critical point. It's concave down. That is clearly a relative max. That's a peak. That's a high point. Right? So don't memorize specifically if it's concave up or down. Just draw a little sketch if you have to. Picture it in your head. So I have a couple examples on the back. So it says, find the extreme values, absolute and or relative, for this function on this interval. So whatever you're looking for, you got to find critical points. So we got to find critical points. Take a derivative, 3x squared minus 6x, set equal to 0, undefined. Factor it to find your roots. So 0 and 2. So these are your critical points. And then, we could do, to find relative maxes and mins, we could do a first derivative test. And that would involve a line check. Label your line check, please. Put the critical points on there. Watch out for bounces off the graph. Test a value. Say, I like to test far right. Positive. It's positive, negative, positive. So we're not looking for true or false. Positive, negative, positive. And then I usually draw these little lines. And you could even, there's a lot of information you can get from this. Increasing, decreasing. Increasing. It's critical point. This is relative max. This is relative min. Right? Lots of information. Or you could do second derivative test. Now, we usually don't do second derivative test unless we can do first derivative test. So I'm going to do it here, but it's really silly to do this because it's extra work beyond first derivative test. So second derivative test is more of an alternate for when first derivative test doesn't work for some reason. Now, you would do the same work, okay, but then you would plug the critical points in to figure out what is concave up or down. You could do a line check. I mean, you could. So that's going to be -6, which is negative, which is concave down, which means it's got to be a relative max, right? You can find the concavity at 2. And that's positive, so it's concave up. So it's got to be relative min. So either way, now for absolute maxes and mins, line check doesn't generally work unless it's a special case where there's only one critical point. So I would always use extreme value theorem as much as possible. So you got to put the endpoints, which we have, by the way. By the way, you should use that for all these answers. So if you get an answer outside this, you shouldn't include it in your final answers. Put critical points on there. Your other endpoint, in order would be nice. Plug these into the original function. You can see some people accidentally plugging these in the derivative that they just found, because you would do this work, all this work for all of these. So we plug these in, we get -1, -3, +6 is 2, plug 0 and you get 0, -0 +6 is 6, plug 2 and you get 8, -12 +6 is 2, plug 4 in, you get 64 -48 +6 is 22. So this is the absolute min here. There is only one absolute min value, but it can happen at multiple locations. There can be a tie. And this is the absolute max. So now that 6 right there, by the way, was a relative min, right? Or no, relative max. So we say, okay, the maximum is 22 at x equals 4. So this is the way to write answers for absolute max mins. Say what it is, say where it's at. Minimum is 2 at x equals -1 and 2. And there is a local maximum at, you could say at x equals 0. Now you could also say that's just a location. So we could say the local maximum is at 0, or we could say 0, 6, which was this one right here. We could say a local minimum either at x equals 2 or 2, 2. You wouldn't include the endpoint one. But anyways, these are absolute, by the way. If we don't say absolute, if we don't say relative, local, absolute, it means absolute. So there's a little practice there. Here's another one. Try this one. Find the local extrema. Now it just says local, but maybe we'll take a look at absolute also. See if we can answer that. Now we got to take the derivative. So it's going to be 5/3 x to the, I guess, subtract 1. So it's going to be 2/3 minus 20/3 x to the -1/3. And we're going to set this equal to 0, undefined. Now these are classic problems from last year. People make a lot of mistakes just with the algebra. You're going to factor 5/3 x to the -1/3. You always want to factor out the smallest common exponent. And a negative exponent is smaller than a positive one. Right? Now, when you factor it out, you're dividing, and rules of exponents say you're subtracting this one from this one. So it's 2/3 minus -1/3 gives you positive 3/3. Right? Minus 4. So this x equals 0 and x equals 4 are your critical points. That one is undefined, which means it could be like a sharp corner or something, right? Now, if we did first derivative test, which we're usually going to just do that right off, do a line check. Now, if they have rational exponents, it's the numerator that could tell you if it has like an even power. The other thing to watch out for, is in the original problem, look at domain. These are cube roots, so no issues there. They're all positive exponents, no issues. So I'm going to test the value. 5, positive, negative, positive, increasing, decreasing, increasing. Critical point, relative max. Critical point, relative min. So, now if we want the actual values, we know where they're at. But if you want the actual value, that's the y value, then you'd have to plug 0 back into the original equation, and you get 0. You have to plug 4 back in, and you get 4 to the 5/3 minus 10, 4 to the 2/3. We could try and simplify this. Cube root of 4/5, and then 10 times cube root of 4 squared. Now we could take 4 to the 3rd out of that. So that'd be 4. Cube root 16 minus 10 cube root 16. But 16 you could take an 8 out of. So this is just a little algebra simplification. So you take another 2 out. 4 times 2 is 8. Cube root 2. 10 times 2 is 20. Cube root 2. So we get negative 12 cube root 2. So get that. So the local maximum is 0, or you could say it's at 0, 0. Local minimum is negative 12 cube root 2, or you could say it's at this ordered pair, 4 comma negative 12 cube root 2. Now here's the deal. We can't do extreme value theorem because there are no endpoints. That doesn't mean there aren't absolute maxes and mins, but if you look at this graph goes up forever, this graph goes down forever. So there's no max because it goes up forever, and there's no min because it goes down forever. Now, if there was just a single critical point, then we could probably make a decision. We might be able to make a decision about having an absolute max or an absolute min. But graph, by the way, looks like this, just if you're curious. It's kind of like that. So here's your relative max, here's your relative min. So there you go. On today's assignment out of the book, just because you can't use EVT doesn't mean there won't be an absolute max min. It just means you can't use EVT and you're not guaranteed to get an absolute max min. So try these problems, check all your odds in the back of the book, show your work, and let's refresh our memory of these.